In module 4, we have learned about orthogonal property of Legendre's polynomial, also the Rodrigues formula. In module 5, we will discuss about the Legendre's function of second kind. Please note, the Legendre's function of second kind is an infinite series and hence all the calculations has to be done very carefully. We will see about some alternative expressions for Legendre's polynomial on second kind in this module. We will also look into the recurrence relation along with some very good examples. Legendre's function of second kind, which is denoted by q and x. We first obtained some alternative expression for q and x and q dash nx. From definition, we get q and x is equal to n factorial divided by 1.3.5.2n plus 1 multiplied by x to the power minus of n plus 1 plus n plus 1 into n plus 2 divided by 2 into 2n plus 3 x to the power minus of n plus 3 plus dot dot dot. We next multiply both numerator and denominator by 2.4.6.2n and we get equation number 1, which is n factorial into 2 to the power n into n factorial divided by 2n plus 1 factorial multiplied by x to the power minus of n plus 1 plus n plus 1 into n plus 2 divided by 2 into 2n plus 3 x to the power minus of n plus 3 plus dot dot dot, which after simplification gives equation number 2, which is 2 to the power n into n factorial divided by 2n plus 1 factorial multiplied by n factorial into x to the power minus of n plus 1 plus n plus 2 factorial multiplied by 2 into 2n plus 3 x to the power minus of n plus 2 plus 1 plus dot dot dot. And if we put it in the generalized form, we will get equation number 3, which is equal to 2 to the power n into n factorial divided by 2n plus 1 factorial summation r equal to 0 to infinity n plus 2r factorial x to the power minus of n plus 2r plus 1 divided by 2.4.2r 2n plus 3 2n plus 5 dot dot 2n plus 2r plus 1. We put this under the result 1, that is q n x is equal to 2 to the power n into n factorial divided by 2n plus 1 factorial multiplied by this whole expression. If you differentiate result 1 with respect to x, we will get expression number 4, which is q dash n is equal to minus of x 2 to the power n into n factorial divided by 2n plus 1 factorial summation r equal to 0 to infinity n plus 2r plus 1 factorial n to the power minus n plus 2r plus 2 divided by 2 to the power r factorial 2n plus 3 2n plus 5 dot dot 2n plus 2r plus 1. We replace n by n minus 1 in 4, and if you do that, you will get equation number 6 after simplification, which is q dash n minus 1 is equal to minus of 2n 2 to the power n minus 1 factorial divided by 2n minus 1 factorial into 2n summation r equal to 0 to infinity n plus 2r factorial x to the power minus n plus 2r plus 1 divided by 2 to the power r factorial 2n plus 1 2n plus 3 dot dot 2n plus 2r minus 1. We put this result under the name result 2, that is q n dash n minus 1 x is equal to minus 2 to the power n into n factorial divided by 2n factorial multiplied by this expression given in equation number 7. We replace n by n plus 1 in equation number 4 and we will get q dash n plus 1 x is equal to minus 2 to the power n plus 1 into n plus 1 factorial divided by 2n plus 3 factorial multiplied by this expression given in equation number 8. We put it under the result 3, that is q dash n plus 1 is equal to minus 2 to the power n into n factorial divided by 2n factorial multiplied by summation r equal to 0 to infinity n plus 2r plus 2 factorial x to the power minus n plus 2r plus 3 divided by 2 to the power r factorial 2n plus 1 2n plus 3 dot dot 2n plus 2r plus 3 given by expression number 10. We have just derived few alternate expressions for Legendre polynomials of second kind, namely Qnx, Q dash n and Q dash n plus 1. Next we will see how we use these results 1, 2 and 3 in the recurrence relation and its proof. We will also solve one or two examples which will highlight the use of Legendre's polynomial of second kind. We now prove the recurrence relation Q dash n plus 1 minus Q dash n minus 1 is equal to 2n plus 1 into Qn. We start by taking the expression Q dash n minus 1 plus 2n plus 1 into Qn, and we substitute the values of Q dash n minus 1 and Qn from result 1 and result 2, and if you do that you will get the expression number 12. After simplification we get equation number 14, which is equal to 2 to the power n into n factorial divided by 2n factorial summation r equal to 0 to infinity n plus 2r factorial x to the power minus n plus 2r plus 1 divided by 2 to the power r factorial 2n plus 1 2n plus 3 dot 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 2n plus 2r plus 1 multiplied by 2n plus 1 minus 2n plus 2r plus 1, which after simplification gives equation number 15, which is equal to 2 to the power n into n factorial divided by 2n factorial summation r equal to 0 to infinity minus 2r n plus 2r factorial x to the power minus n plus 2r plus 1 divided by 2 to the power r factorial 2n plus 1 2n plus 3 dot 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 2n plus 2r plus 1. We simplify the expression and we get equation number 17, which is equal to minus 2 to the power n into n factorial divided by 2n factorial summation r equal to 1 to infinity n plus 2r factorial x to the power minus n plus 2r plus 1 divided by 2 to the power r minus 1 factorial 2n plus 1 2n plus 3 dot 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 2n plus 2r plus 1, which is equation number 17. Please note, in equation 16 this 2 and this 2 to the power r and this r factorial cancels to give you 2 to the power r minus 1 and r minus 1 factorial, and that is why the summation starts from r equal to 1 to infinity. We then replace r by s plus 1 and we obtain equation number 18, which is nothing but the expression of q dash n plus 1, which is derived in result number 3. And this completes the proof for example 1. In example 2, we prove another recurrence relation 2n plus 1 into x qn is equal to n plus 1 qn plus 1 plus n qn minus 1. We start with the expression n into qn minus 1 minus 2n plus 1 x qn. We substitute the values of qn minus 1 and qn from previous expressions and we get expression number 22. After simplification, we come to equation number 25, which is 2 to the power n into n factorial divided by 2n plus 1 factorial summation r equal to 0 to infinity n plus 2r minus 1 factorial x to the power minus of n plus 2r divided by 2 to the power r factorial 2n plus 3 2n plus 5 dot 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 2n plus 2r plus 1 multiplied by n into n plus 2r plus 1 minus 2n plus 1 into n plus 2r. Which can be put in a more simplified form as shown in equation number 27, which is equal to 2 to the power n into n plus 1 factorial divided by 2n plus 1 factorial summation r equal to 1 to infinity n plus 2 r minus 1 factorial x to the power minus n plus 2 r divided by 2 to the power r minus 1 into r minus 1 factorial 2n plus 3, 2n plus 5 dot 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 2n plus 2 r plus 1. Please note, in equation number 26, this 2 to the power r and this r factorial, they got cancelled this with this 2 r, which gives you 2 to the power r minus 1 into r minus 1 factorial, and that is why the summation starts from r equal to 1 to infinity. In equation number 28, we substitute r by r plus 1 and we get the expression which is given in 28. After simplification, we arrive at equation number 30, which is minus n plus 1 2 to the power n plus 1 factorial divided by 2n plus 3 factorial summation s equal to 0 to infinity n plus 2s plus 1 factorial x to the power minus n plus 2s plus 2 divided by 2 to the power s factorial 2n plus 1 dot 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 2n plus 2s plus 3, and this expression is q n plus 1, and hence we get n q n minus 1 minus 2n plus 1 into x q n is equal to minus n plus 1 q n plus 1 as given in equation number 31. After rearranging, we get 2n plus 1 into x q n equal to n plus 1 q n plus 1 plus n q n minus 1, which is our desired result. We move to another recurrence relation, x q n dash minus q n minus 1 dash is equal to n q n. We have already shown that n plus 1 q n plus 1 minus 2n plus 1 x q n plus n q n minus 1 is equal to 0. We now differentiate equation 33 with respect to x, and we obtain equation number 34, which is n plus 1 q dash n plus 1 minus 2n plus 1 x q n dash plus q n plus n q dash n minus 1 equal to 0. We now use the value of q dash n plus 1 from the recurrence relation. Please see example 1, which is q dash n plus 1 equal to q dash n minus 1 plus 2n plus 1 q n, and we get equation number 36, which is 2n plus 1 q n minus 1 minus 2n plus 1 x q dash n plus 2n plus 1 q n n plus 1 minus 1 equal to 0. And if you cancel 2n plus 1 from all these three terms, you arrive at equation number 37, which is x q dash n minus q dash n minus 1 is equal to n q n, which is what we have to prove. Let us now move to example 4, where we prove the recurrence relation 2n plus 1 into 1 minus x square q dash n is equal to n into n plus 1 q n minus 1 minus n q n plus 1. Since q n x is Legendre's function of second kind, it is going to satisfy the Legendre's equation given in 38. And if it does that, we substitute y by q n x and we get the expression 39, which is d dx of 1 minus x square q dash n is equal to minus n into n plus 1 q n. We now integrate both sides of 39 between minus infinity to x, and we get 1 minus x square q dash n from infinity to x is equal to minus n into n plus 1 integration infinity to x q n x dx. And this gives equation 40, which is 1 minus x square q dash n is equal to minus n into n plus 1 integration from infinity to x q n x dx, because as x tends to infinity, q dash n x is equal to 0. We now use the recurrence relation q dash n plus 1 minus q dash n minus 1 is equal to 2n plus 1 q n, which is given in equation 41. We integrate both sides of 41 between infinity to x, and we obtain q n plus 1 minus q n minus 1 from infinity to x is equal to integration of infinity to x 2x plus 1 q n dx. If we expand it, we get q n plus 1 x minus q n minus 1 x is equal to 2n plus 1 into integration infinity to x q n dx, because as x tends to infinity, both q n plus 1 x and q n minus 1 x are 0, and this is due to the fact that both the expressions contain x as a negative power. So, as x tends to infinity, x to the power minus n tends to 0. Now, from equation 40 and 42, we get 1 minus x square q dash n is equal to minus n into n plus 1 q n plus 1 minus q n minus 1 divided by 2n plus 1, and if we rearrange the terms, we will get equation number 44, which is 2n plus 1 into 1 minus x square q dash x equal to n into n plus 1 q n plus 1 x minus q n minus 1 x, which is our desired result. We now look into the recurrence relation, which we have to prove here. Q dash n x minus x into q dash n minus 1 x is equal to n into q n minus 1. Please see example 1, where we have proved q dash n plus 1 minus q dash n minus 1 minus 2n plus 1 q n equal to 0. If we rearrange the terms, we will get expression number 46. We multiply both sides of 45 by x and subtracting it from 46, we get n plus 1 q n plus 1 minus x q dash n plus 1 plus x q dash n minus 1 plus n into q n minus 1 equal to 0. We now use the recurrence relation n q n is equal to n q dash n x minus q dash n minus 1 x. We replace n by n plus 1 in 48, and then substituting in 47, we get n q dash n plus 1 minus q dash n x minus n into q dash n plus 1 plus x into q dash n minus 1 plus n q n minus 1 x is equal to 0, and if we simplify, we will get the result as q dash n x minus x q dash n minus 1 is equal to n into q n minus 1 x, which is our desired result. Our final example is, we have 4 parts of it. The first part is, we have to prove x square minus 1 multiplied by q n p dash n minus p n q dash n is equal to c, where c is a constant. The second part, we have to prove q n by p n is equal to integration x to infinity dx divided by x square minus 1 p n whole square, and hence we have to deduce q 0 x is equal to half of log x plus 1 divided by x minus 1, and q 1 x is equal to x by 2 log of x plus 1 by x minus 1 minus 1. Let us see about the solution of the first part, which is x square minus 1 q n p dash n minus p n q dash n is equal to c, which is a constant. Since p n x and q n x both satisfy the Legendre's equation, we will get equation 49 and equation 50, which is 1 minus x square p n double dash minus 2 n p n dash plus n into n plus 1 p n equal to 0, and likewise with q n, which is given in equation number 50. Now, we multiply equation 49 by q n and 50 by p n, and subtracting, we will get equation number 51, which is 1 minus x square p n double dash q n minus q n double dash p n minus 2x p n dash q n minus q n dash p n equal to 0, and after simplification we will arrive at equation number 53, which is d dx of 1 minus x square p n dash q n minus q n dash p n equal to 0, and which on integration will give you 1 minus x square p n dash q n minus q n dash p n plus c equal to 0, and hence we get our desired result, that is x square minus 1 p n dash q n minus q n dash p n is equal to c, where c is an arbitrary constant. We now move to the second part of the problem, where we have to prove q n by p n is equal to integration x to infinity dx by x square minus 1 p n square. We start with equation number 55, which can be rewritten as p n dash q n minus q n dash p n is equal to c by x square minus 1, which is equal to c by x square into 1 minus 1 by x square whole to the power minus 1. If we expand this in binomial, we will get c by x square 1 plus 1 by x square plus 1 by x to the power 4 plus dot dot dot, which is given in equation 56. We now use the definition of Legendre's polynomial of first kind and Legendre's function of second kind. We put these values in this particular expression on the left hand side, and if you do that, you will get expression number 57. What we are doing here is we are finding out the value of this constant c. So, what we will do is we will equate the coefficient of 1 by x square from the right hand side and also from the left hand side. As you can see, in the right hand side the coefficient of 1 by x square is c. Let us find what is the coefficient of 1 by x square in the left hand side. So, the left hand side is given by the expression as you can see in equation 57. Please note the expression x to the power minus n plus 1 and n into x to the power n minus 1, if you multiply these two, you will be getting the coefficient of 1 by x square. Similarly, in the second case, if you multiply x to the power n and x to the power minus n plus 2, you will be getting the coefficient of 1 by x square. And if you find that the coefficient of 1 by x square in the right hand side of 57 will be given by n factorial divided by 1.3.5 into 2n plus 1 into 1.3.5 into 2n minus 1 by n factorial into n minus 1.3.5 dot 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 2n minus 1 divided by n factorial into n factorial by 1.3.5 2n plus 1 into minus n minus 1, and if you simplify that, you will be getting the value 1, and hence the coefficient of 1 by x square in the right hand side of 56 is c, implying that c is equal to 1. Therefore, we arrive at equation 59, which says x square minus 1 p n dash q n minus q n dash p n is equal to 1. You divide both sides by p n square and you get equation 60. The left hand side of 60 can be expressed as d dx of q n by p n, and the right hand side is minus 1 by x square minus 1 p n square. We integrate 61 with respect to x from infinity to x, and we get q n by p n from infinity to x is equal to minus of infinity to x dx by x square minus 1 p n square, which is equal to q n x by p n x minus limit x tends to infinity q n by p n is equal to integration x to infinity dx by x square minus 1 p n square, given by equation 63. Now, by L'Hopital rule, we can calculate limit x tends to infinity Qn by Pn, which is equal to limit x tends to infinity the nth derivative of Qn divided by the nth derivative of Pn. And if you do that, you get what is given in equation number 65. In equation number 65, please note that the power of x is minus of 2n plus 1. So, as x tends to infinity, x to the power minus 2n plus 1 tends to 0, hence the answer of this limit is 0. And thus, we arrive to our conclusion that Qn by Pn is equal to integration x to infinity dx by x square minus 1 Pn square, which is our desired result. We now look into two corollaries which we have to prove, which comes along with the main problem. In the previous expression 66, which is also given here, we have to put n equal to 0, and if you do that, you get q0 by p0 is equal to integration x to infinity dx by x square minus 1 p0 square. Please recall that the value of p0 is 1, and if you substitute that, you will be getting equation 68, which is integration x to infinity dx by x square minus 1. If we integrate that, it will come to half of log x minus 1 divided by x plus 1 from x to infinity. If we substitute the values, you will be arriving at equation number 70, which gives half of log x plus 1 divided by x minus 1, because as x tends to infinity, log of x minus 1 divided by x plus 1 can be expressed as log of 1 minus 1 by x divided by 1 plus 1 by x, and as x tends to infinity, 1 by x tends to 0, and we all know that log 1 is equal to 0. And hence, we get the result as q0 by p0 is equal to half of log x plus 1 divided by x minus 1. Our second part, we put n equal to 1 in the expression Qn by Pn is equal to integration x to infinity dx by x square minus 1 Pn square. And if you do that, you will be getting Q1 by P1 is equal to integration x to infinity dx by x square minus 1 P1 square. And we know that P1x is equal to x, and if you substitute that, you will be getting equation 73, which is Q1 by x is equal to integration x to infinity dx by x square minus 1 x square. To integrate this, we define the integrand in partial fraction, which is given in equation 74, which is 1 by x square minus 1 minus 1 by x square. And if you integrate, you will be arriving at 75, which says q1x is equal to minus x multiplied by half of log x minus 1 by x plus 1 by x. And in the similar fashion, limit x tends to infinity, log of x minus 1 by x plus 1 is equal to 0. And after simplification, we arrive at equation number 76, which is x by 2 log of x plus 1 by x minus 1 minus 1, which is our desired result. With this module, we come to the end of the chapter 4, which is Legendre's polynomial. We have started with the basic definition of the Legendre's polynomial, followed by the generating function, the orthogonal properties, Rodrigues formula, recurrence relation, and lastly, a brief description of the Legendre's function of second kind. I sincerely hope that this chapter has helped you learning the basics of Legendre's polynomial. Thank you.